Okay, physics geniuses, this is our video lecture for the final exam review for physics. And so what I'm going to do today is just go through these questions directly, and we will, I'll post this on my YouTube channel, and then the questions that you're going to see, there will be one question from every chapter that we've covered, 16, 17, 18, 20, 21, 22, 23, 24, and 25. Okay, so each one of these questions will correspond to a separate chapter. So I will go ahead and work out the solutions of these problems, and that will be your review. If you have any questions on this, you can email me and we can set up a Zoom call, or we can talk on the phone so we can go through this directly. So let's go ahead and get started. So the first question, we have a transverse wave, and it's going and propagating through a string that has a tension of 60.5 newtons. If the string is 15.9 meters long, then we want to know what the mass is. Okay, so first of all, we need to get the governing equation for this particular item. Okay, so we know that the velocity of a string is equal to the square root of the tension on the string divided by its linear density. Okay, so that B is kind of weird. So if we have the linear density of the string, that is equal to the mass of the string divided by the length. And now we have everything that we need except for the mass of the string. Okay, and that's what we're trying to figure out. So I plug this in, so the velocity of the string is equal to the square root of the tension of the string times the length of the string divided by the mass. Okay, move that over so you can see that a little bit better. Okay, so then I just square both sides and I can solve directly for the mass. So velocity of string squared is equal to the tension of the string, the length, divided by the mass. Okay, so I just rearrange the equation, and the mass is then equal to the tension of the string in newtons divided by the length divided by the velocity of the string squared. Okay, so the tension of the string we're given as 60.5 newtons. The length of the string is 15.9 meters. And the velocity of the string is, I have to look back at the problem, 43.2 meters per second. So that gives me meters per second, and I've got to square that too, don't I? So I go to my calculator. 60.5 newtons times 15.9 meters divided by 43.2 quantity squared. That gives me a mass of the string of 0.52 kilograms. Okay, just to do a little dimensional analysis here, see if I can bring that over. It's a little difficult to see. 0.52 kilograms. So if we do some dimensional analysis, then you can show that a Newton is equal to a kilogram meter per second squared. So if I put that in, then that gives me kilogram meter per second squared times meter divided by meters squared per second squared. Then meters on top cancel with meters squared in the bottom. Sorry, move that down a little bit. And then second squared just gives you kilograms as your final answer. Okay, so that's the first problem. Let's go ahead and look at the second problem. Second problem is a violin with a string length of 32 centimeters and a string density resonates with the first 1.5 grams per centimeter, resonates with the first overtone of an organ pipe with one end closed. The pipe length is 2 meters. Okay, so this is our first overtone. Tension in the string is going to be equal to. So we know in this particular problem that the frequency that the violin string is moving is equal to 1 over twice of its length times the square root of the tension of the string divided by the linear density of the string. Okay, so we can figure out what that, we know everything in here except for the tension in the string. So, but we also know that the frequency of the violin string also has to be the same frequency that's in the pipe. Okay, so that frequency is given as m times the velocity, and that's the velocity of sound, over 4L, of the, and that's the length of the pipe. So I'm going to put L sub P for length of pipe. Okay, so M here is for the first overtone, okay? And that first overtone then has, that's your fundamental frequency of 1, so that just equals the velocity, and that's the velocity of sound, divided by 4 times the length of the pipe, okay? The pipe length is 2 meters, and the velocity of sound is 343 meters per second, approximately. So that gives me the pipe length of 2 meters, and I calculate that out. I just take 383 divided by 4 divided by 2, and that gives me a fundamental frequency of 42.9 approximately hertz. Meters cancel, and that leaves reciprocal seconds, which is hertz. Okay, so now I can use this to back solve the tension of the string, because I know that 42.9 hertz is equal to 1 over 2 times the length of the string divided, times the tension of the string, square root, divided by the linear density. Okay, so I know my string length is 32 centimeters, and well, wait a minute, let me go ahead and rearrange this so I can solve for the tension of the string. Okay, so 42.9 hertz times 2 times the length of the string is equal to the square root of the tension of the string divided by mu. So I just take the square of both sides, and that gives me 42.9 hertz times 2 times the length of the string squared equals the tension of the string divided by mu, the linear density. Okay. Then all I need to do is multiply both sides by mu. I just have tension of the string is equal to mu times 42.9 hertz times 2 times the length of the string, quantity squared. Okay, mu is linear density. Okay, and that's given in grams per centimeter. So I have to convert that to 1.5 grams per centimeter. So I know that for every 1 kilogram, there are 1,000 grams. And I know that for every 100 centimeters, there's 1 meter. Okay. So grams cancel, centimeters cancel, and I get kilograms per meter. Then I take 42.9 hertz times 2 times the length of the string. And that's 32 centimeters, so that's 0.32 meters. Quantity squared. Okay, I can just plug this into my calculator. You can see the whole thing there. Okay. Okay, plug this into my calculator. So I have 42.9 hertz times 2 times 0.32. Take that squared times 1.5 grams per centimeter divided by 1,000 grams, or 1,000 grams, times 100 centimeters. And that gives me a tension of the string of 113 newtons. Okay, I can do a little dimensional analysis over here. Basically, I've got kilograms per meter. Hertz is reciprocal seconds. So that gives me kilograms meter per second squared, which gives me a Newton. Okay, so we can move on to the next problem. So this is more in terms of light. Let's say, and this figure goes to problem 4, not problem 3. So I have a 2-slit arrangement with 60.3 micron separation between the slits. My light is 482 nanometers, and the viewing screen is 2.14 meters away. And I want to find the distance from the first dark fringe on one side of the central maximum to the second dark fringe on the other side of the central maximum. Okay, so looking in my book, then I find out the equation that I want for dark fringes is y prime m, that's the position of the dark fringe, is equal to m plus 1/2 times lambda, the wavelength of light, times L, which is the distance to the screen, divided by D, which is the distance between the two slits. Okay, so if I want to find delta Y1, that's just the distance from the central maximum to the first dark fringe, okay? So what that would be, or actually that would be delta Y0, because I would be starting at 0 and looking at just half of the distance from the central maximum of the central maximum. So I just plug in 0 plus 1/2 times lambda, which is 482 nanometers. So I take 482 times 10 to the negative 9th meters. My length is 2.14 meters. And then my distance between the slits is, I have to look, is 60.3 microns, which is 60.3 times 10 to the negative 6 meters. Okay, so I plug this all in my calculator. .5 times 482 times 10 to the negative 9th times 2.14 meters divided by 60.3 divided by 10 to the negative 6, and that gives me 0.00855 meters, or 8.55 millimeters. Okay, show you that over there. Okay, so that's my first distance. Now I need this distance on the other side to the first dark fringe. Okay, so I want delta y1, which is 1.5 times this same thing. So if I calculate that quickly, move that over a little bit. Here we go. Didn't realize that wasn't all on the screen. Okay. And that gives me 25.65 millimeters. So then delta y0 plus delta y1 is equal to 8.55 millimeters plus 25.65 millimeters. And that gives me 32.4 millimeters as the distance. Okay, so for the next problem then, we have a ray of glass that makes at a glass water interface of an angle of 48 degrees from the normal. Okay, when the ray of light interacts with the glass and the water interface, then the angle changes to 68 degrees. Okay, the index of refraction of water is 1.33, and if we have a different ray in the glass, which is 29, then we want to know what the angle of refraction of is in the water. Okay, so the thing that we're missing here is the angle of refraction in the glass. Okay, and we know that due to Snell's law, that the index of refraction is related to the sine of the angle of the incident radiation and the exiting radiation. Okay, so N1 sine theta 1 is equal to N2 sine theta 2. Okay, so in the first instance, we're given both angles. We know for water, we have 1.33, and our angle in the water is 68 degrees. We don't know the index of refraction of the glass, but we know that the angle there is 48 degrees. Okay, so we can back solve just by taking the sign and just say N2 is equal to 1.33 times sine 68 divided by sine 48 degrees. Okay, so that can give us the index of the refraction of the glass. So we go ahead and plug that into our calculator. So we take 68 on top, sine times 1.33 equals, divided by 48 sine, and that gives us an index of refraction of the glass is 1.66. Okay, then to find out the index of refraction, or then we find if we have incident radiation in the glass, and we want to find out the radiation in the water, now we're solving for theta 1. So 1.33 times sine theta 1 is equal to 1.66 times sine of 29 degrees. Okay, so we just rearrange this and we solve for sine of theta 1, and then we take the arc sine of that. So sine theta 1 is equal to 1.3366 divided by 1.33 times sine of 29 degrees. Okay. And that gives us the sine of theta 1 is 0.605. And if I take the arc sine, then theta 1 is 37.2 degrees. Okay, so we just did that entire problem using Snell's law. Okay, for the next problem, you have a proton located at x equals 1 nanometer and y equals 0 nanometers. And then you have an electron that's located at x equals 0 nanometers and y equals 1 nanometer. Okay, and you want to find the attractive Coulombic force between the two of them. Okay, and the value for K is given there. Okay, so for this instance, we know that the force between them is equal to K times the absolute value of Q1 and the absolute value of Q2, all divided by R squared. Okay, so Q1 we know and Q2 are both 1.6 times 10 to the negative 19th coulombs. Okay, that's just the absolute value of those two. So we can say that Q1 absolute value equals Q2 absolute value equals that. Okay, and then the radius, we know if we plot these out, that the proton is on x equals 1 and y equals 0, and the electron is on x equals 0 and y equals 4. Okay, So the distance between these two, if I just use Pythagorean theorem, is just the hypotenuse of that triangle. So I take 4 squared plus 1 squared, and that gives me a hypotenuse of square root of 17. Okay, so my radius is square root of 17. So then all I need to do then to find the force is just say force is equal to 9.0 times 10 to the 9th Newton meter per Coulomb squared times 1.6 times 10 to the negative 19th coulombs. And since the charge is the same, but just opposite signs, and I'm taking absolute value, I can just square that term. Okay. And then I take the radius squared. So the square root of 17 squared is just 17. But that is 17 what? That is 17 nanometers. So I have to take 17. That's not as easy as I thought, is it? Okay. So it's square root of 17 times 10 to the negative 9th nanometers, quantity squared. Okay, so it's a little hairier than that. So I plug this into my calculator. I'm going to do the denominator first. So 17, take the square root of that. Okay, times 10 to the negative 9th. Okay. And that gives me nanometers. Then I take that quantity squared. And that gives me 1.7 times 10 to the negative 17th. Okay, take the reciprocal of that. Times 9 times 10 to the 9th. Times 1.6 times 10 to the negative 19th. Squared. That gives me 1.35, actually 1.36 times 10 to the negative 11th newtons. Okay, and that should be meters, not nanometers. Okay, 1.36 times 10 to the negative 11th newtons. So a little bit of attractive force there, but not much, but we're considering that these are electrons. Okay, so let's go to number 6. So then we have a proton that has a speed of 2 times 10 to the 5th meters per second, and it falls through a potential difference V, and it increases its speed to 4.0 times 10 to the 5th meters per second. So we want to find what's the potential difference through which the proton fell. Okay, so we know that V1 is equal to 2 times 10 to the 5th meters per second. V2 is equal to 4 times 10 to the 5th meters per second. Okay. So the difference in kinetic energy has got to be the difference in the potential energy, because delta potential energy plus delta kinetic energy equals 0. Okay, so delta potential energy is just going to be Q, the charge of the proton, times the change in voltage or the change in potential, plus delta kinetic energy is just going to be the mass times velocity 2 squared divided by 2 minus mass times velocity 1 squared divided by 2 equals 0. So now all I have to do is go ahead and solve. I know the kinetic energy of my particle, of my proton. I know my charge of my particle. So now I just need to solve for delta V. So delta V is equal to mv1 squared over 2 times mv2 squared over 2 all divided by Q, the charge. Okay, I can simplify that a little bit further. Just take out M divided by 2Q V1 squared minus V2 squared, and that will give me the potential difference. Okay, so then I just plug in numbers there. My mass of a proton is 1.67 times 10 to the negative 27th kilograms divided by 2 times the charge. And the charge is 1.6 times 10 to the negative 19th coulombs. Okay, my first velocity is 2.2 times 10 to the 5th meters per second. I want to square that. Minus 4 times 10 to the 5th meters per second. I want to square that. Okay, so I plug this into my calculator. And the voltage drop that I get is negative 626.25 volts. Okay. So that gives me then kilogram meter squared per second squared over coulomb. Kilogram meter squared per second squared is just a Newton meter, which is a joule. So that gives me joules per coulomb, which is a volt. Okay, so let's go ahead and move on to the next problem. Okay. Say we have a voltage difference and it's applied to a piece of copper wire and a current of 5 milliamps flows. Let's say if the copper wire is replaced with a silver wire and the silver wire is twice the diameter of the copper wire, how much current will flow through the silver wire? The lengths of both wires are the same and the voltage difference remains unchanged. Okay, so we know the resistivity of the copper and the resistivity of the silver, so we can go ahead and solve this problem. Okay, but we know that the resistance of the wire is equal to rho, which is resistivity, times the length divided by the cross-sectional area of the wire. Okay, so for R for copper, resistance for copper, that's just equal to resistivity 1.68 times 10 to the negative 8 ohm meters. The length we don't know, so we'll just leave that as L. And the area we know for the copper wire we'll just call A. Okay. And then the resistivity for the silver wire is R sub silver. So that's 1.5959 times 10 to the negative 8 ohm meters times our length divided by a new area. But now our new area, we can get this to hold still. Our new area is an area with twice the diameter. Okay, so we're going to take the diameter squared over 2. And so that is going to be 4 times A. Okay. Okay, that's not holding still very well. Okay. So then, let me see if I can focus that. Focus. Okay, there it goes. So we know that silver is going to provide, it's going to be a larger wire, so it's going to have less resistance to that particular wire. And we know that the current in the copper wire is equal to the voltage drop across the copper wire divided by the resistance of the copper wire. Okay. And we know that the silver wire, the current in the silver wire, is equal to the change in voltage, which is the same in both wires, times the resistivity of the silver. So now, since we know that the voltages are going to be the same, then we can just say that delta V is equal to the current in the copper wire times the resistance of the copper wire. It's also equal to the current in the silver wire times the resistance of the silver wire. Okay, so if we know that, we know that the current in the copper wire is 5 milliamps. And we know that the resistance of the copper wire is 1.68 times 10 to the negative 8 ohm meters times L divided by A. And this is equal to I sub S, which is the current in the silver wire, which we don't know, times 1.59 times 10 to the negative 8 ohm meters times L divided by 4A. Okay, so if we look at this, then we can start to cancel things out, and then this will start to take shape. Since A is on both sides of the equation in the denominator, we can get rid of that. And L is on both sides of the equation in the denominator, we can get rid of them. Okay. And so if we solve then for I sub S, then that's just going to be the left-hand side of the equation. Times 4 divided by 1.59 times 10 to the negative 8 ohm meters. Okay. And then if we calculate that out, so I've got 5 milliamps, or 0.005 amps, times 1.68 times 10 to the negative 8 times 4 divided by 1.59 divided by 10 to the negative 8. Oops, screwed up. Okay, and that gives me 21.1 milliamps, or 0.0211 amps. Okay, so that's problem number 7. Then for problem number 8, we have one of these good old circuits and resistors. Okay, so we want to know what's the current that is going through resistor 1 in the circuit. Okay. And so if you look at this particular problem, then we have, on the first branch, we have a 3-volt step up. And then 100 ohm resistor. On the second branch, we have a 7-volt step up. And on the third branch, we have a 200 ohm resistor and a 150 ohm resistor. Okay, so the voltage drop over each one of these branches has to be 7, right? Okay, because you've got 7, you're stepping up 7 here, stepping up 3 here. Okay. So then you're burning off basically 4 volts here. So in this particular problem, then you're stepping up 3 volts here, and then in order to maintain the same here and have the same voltage nodes, then you have to step up 4 volts here. So you have a 4-volt voltage gain across this resistor here, and that voltage gain is going to result in a current that actually flows the opposite direction. So the current I is just going to equal 4 volts divided by 100 ohms. Okay, so that will be 0.04 amps, and 0.04 amps will then be going in the opposite direction of the battery. Okay, so this current I1 will be moving in that direction. Okay, pretty simple problem. Okay, next we have a 5-meter length of wire carrying 5 amps, lies in a horizontal table with a rectangular top with dimensions 0.3 meters and 0.4 meters. The ends of the wire are attached to opposite ends of the diagonal of the rectangle. The vertical magnetic field coming out of the table is 0.3 Tesla, and we want to know what is the magnetic force that acts on this segment of wire. Okay. So we have a horizontal table. And we have our wire here, our copper wire. Okay. Magnetic field is coming out of the table. Okay. Current is 5 amps. Okay. The vertical magnetic field B is equal to 0.3 Tesla. Okay. And the angle, if they're trying to trip you up here, but the angle that you're seeing is actually a 90-degree angle, even though this is on the diagonal. But the length of wire L, in this instance, is just 0.5 meters, because this is a 3, 4, 5 triangle. Okay. So once you're given that, and then the angle between the magnetic field and the wire itself, theta, is equal to 90 degrees. So we know that the current carrying wire, get me out of there. Okay. That the current carrying wire then, the force on the wire is going to equal to pi times the length of the wire times the magnetic field times sine theta. Okay, since it's coming vertically out, sine theta again is 90 degrees. So then we just put the current as 5 amps. The length is 0.5 meters, just on that segment of wire. The magnetic field is 0.53 Tesla, and then sine 90 degrees is equal to 1. So I just take 5 amps times 0.5 meters times 0.3 Tesla, and that gives me 0.75 newtons as my force. Okay, let's go on to the last problem. Let's say we have, this is only problem from chapter 25. We have a tightly wound solenoid, circular cross-section. It has 180 turns, and it has a change in the internal magnetic field of 3 Teslas per second, and that causes 6 amps of current to flow. We know that the resistance of the solenoid is 17 ohms, and the only EMF source is the fact that the magnetic field is changing, and that's creating 6 amps of current. So we want to know the radius of that particular solenoid. Okay, so we know in this particular instance that our electromotive force is going to equal to the number of turns of our solenoid times our flux over time, delta V over delta time. Okay. Now N then is equal to 2 pi of our radius times delta B, the change in magnetic field, over delta T. Okay, so I know the number of turns. I have N equals 180 turns. And I know delta B over delta T is 3 Tesla per second. And I know what E is. E is just my current times my resistance. And my current is 6 amps. And my resistance is 17 ohms. Okay. So 6 amps times 17 ohms gives me a total voltage E of 102 volts. Okay. And so now I know the number of turns, I know delta B over delta T, I can solve for 2 pi r squared, or pi r squared. So 102 volts is equal to 180 turns times pi r squared times 3 Tesla per second. Okay, so I just isolate R then. So R is equal to 102 volts divided by 180 turns divided by pi divided by 3 Tesla per second. And then let's take the whole square root of this entire quantity. And that gives me a radius of my coil of 0.245 meters, which equals 24.5 centimeters. Okay, so that's my coil, that's my coil's radius, and I was able to calculate electromotive force. I was given the number of turns, and I was given the magnetic strength, and so that gives me my answer. And that concludes the video review for the physics final exam. If you have any questions, please email me and we can set up a time to talk on Zoom. The final exam itself will be on Monday, April 20th. I'll email you the final exam at 8 a.m. and then it's due by 5 p.m.